Good morning, everyone. I am Dinesh Ec Aat from the IT department, section A. Today, I am going to tell about the topic engineering chemistry. The topic name is types of zeolite membranes. Introduction: Zeolite membranes overview. Zeolite membranes are crystalline substances with uniform nanocurrents enabling molecular savings. Their framework consists of silicon O4 and aluminum O4 tetrahedra, linked with the way oxygen atoms forming 3D porous networks. Ion action capacity arises from A subtraction, introducing negative charge balanced by cations. Example, sodium, potassium. Thermal stability up to 800 degrees Celsius and chemical intenses in acidic or basic environments make them ideal for hash separations. Membranes are synthesized with hydrothermal crystallization on porous supports. Stainless steels example. MF5 type zeolite membranes. MF5 has orthogonal symmetric with straight and sinusoidal channels. Silicon or aluminum ratio controls hydrophilicity. Low ratios 1 to 50 enhances water adsorptions. High ratios greater than 200 favor organics. Performance follows Knudsen diffusion, but deviations occur due to the framework flexibility and adsorption. Used in xylene isomer separation and CO2 CH4 gas separation. Defects: reduce the selectivity post synthesis cancellation, remove template molecules. FAU type zeolite membranes. FAU zeolite has large 0.74 nm supercharges connected via 12 rings windows. High silicon or aluminum ratios reduces cation density, enhancing carbon dioxide and CH4 selectivity. Laminar fischl wood kinetics dominant gas adsorption. Used in air separation, N2 or O2 selectivity 4 to 6, and heavy hydrocarbon dehydration. Thermal expansion mismatch with support causes microcracks, requiring graded interlayer. LDA type zeolite membranes. LDA zeolite has 3D 8 ring spores and alpha cages, ideal for water distillation. Ion action with Cf plus 2 or potassium plus. Tune spore size 3A, 4A, 5A nms. Evaporation flux follows Arrhenius J equal to where EA equal to 20 to 40 kilojoules per molecule of water. These are used in ethanol dehydration and lithium plus recovery for brine. Hydrothermal stability limits long-term operation above 120 degrees Celsius due to framework dealumination. MOR type zeolite membranes. MOR has 1D12 rings and 8 rings, channels causing anisotropic diffusion. High silicon or aluminum ratios improve hydrophobicity, enhancing hydrocarbon or water selectivity. Gas transport follows Maxwell-Stephen equation. Used in xylem is isomer separation and CO2 captures from the flue gases. DDR type zeolite membranes. DDR has 8 ring pores with high selectivity. Rigid framework prevents CH4 adsorption. Adsorption isotherms fit dual site luminar. Used in natural gas sweetening and biogas upgrading. CH type of zeolite membranes. CH has 8 ring pores and Capacitite cages, ideal for small molecule separations. High silicon or aluminum ratios balance CO2 absorption and diffusion. Water induced framework swelling reduces selectivity by 20 to 30%. Used in post-combustion CO2 capture and methanol to olefins. AFI type zeolite membranes. AFI has 1D 12 ring channels with moderate hydrophobicity. Core geometry enables crystalline diffusion for H2 versus CO2 selectivity 4.7. Used in H2 purification and alkane and alkene separation. Thermal stability up to 500 degrees Celsius but degrades in acidic conditions due to aluminum leachings. ETS type Titan oscillate membrane. ETS has 3D 12 rings and 7 rings. Channels with TiO-Ti linkages. TiO4 plus sites creates Lewis acidity enhancing CO2 absorption. Used in CO2 capture and photocatalytic membrane reactors. Anisotropic thermal expansion causing delamination. CTE mismatch with supports. Synthesis requires TiOR4 precursors and HF mineralizers to control crystallinity. Synthesis. In synthesis, crystallization. Supports is immersed in visceral gel. Nucleation follows augmeric kinetics. Defects arises from stress during template removal. Secondary seeded growth. Seed layer is deposited via dip coating or spin coating with colloidal zeolites. Secondary growth in diluted vesicle gel reduces defects and improves intergrowth. Used for large area membranes in industrial modules. Characterization XRD and SEM. XRD confirms phase purity, estimates crystal size from the peak boardings. SEM reveals membranes, thickness, and surface details. TDS maps elemental distribution and confirms absence of intergrowth phases. Gas permutation. Single gas performance is measured via Weichel-Calembach cell. Ideal selectivity, but real sensitivity accounts for defects. Maxwell-Stephen module fits multi-component data. Defects and sealing techniques. Intercrystalline gaps reduces selectivity defect. Density cancellation removes templates but creates cracks due to the thermal stress. Applications gas separation. MFA membranes for xylene isomer separation. DDR membrane for CO2 performance. FAO membrane for N2 performance. CH4 membrane for CO2 permeance. Application liquid separation. LTA membranes for ethanol dehydration. MFA membrane for organic or water separation. Preparation performance follows solution diffusion modules. High flux requires thin membranes. Hybrid systems. Challenges and future directions. Scalability. Current synthesis yields 80% defect free membranes on 10 centimeters 2 scales. Stability is hydrothermal above 150 or 300 degrees Celsius. Cost. Cost to template and support. Account for 60% of total cost. Mixed matrix membranes with zeolites improve flexibility. Case study. Industrial deployment. LTA membranes in ethanol biofuels plants. 100 meter square modules. DDR membranes in natural gas processing. 20 meter square units remove CO2 to 2%. Economic analysis payback period. Thank you for listening this session. Thank you, everyone.